Hello, ladies and gentlemen, and welcome to this talk on HiGrad Py, which is a Python library implementing the hierarchical incremental gradient descent algorithm. Let me start by first introducing myself. I'm Vihan Singh. I'm based out of India, and I recently completed my bachelor's in mathematics and computer science. I run a quantitative trading firm called Black Rose Technologies, where we basically use machine learning, statistics, and computer science to try and make money out of the stock market. Now, the core content of this presentation and the algorithm that's implemented in the Python library is not something I came up with. It was created by Mr. Su and Mr. Zhu. I'll not take the risk of pronouncing their full names to avoid the embarrassment of butchering the pronunciations. About 2 years ago, in 2018, when they were researchers at the University of Pennsylvania, they published a very heavy titled paper called Uncertainty Quantification for Online Learning and Stochastic Approximation via Hierarchical Incremental Gradient Descent. Right. So in that paper, they discussed the HiGrad algorithm, and they also implemented it in a R library of the same name, which is basically what inspired the HiGrad Py library, and which is what I'm here to present. So let me first set the stage by going over how like machine learning basically works. Right. Step one is you choose a model. The model could be something simple like linear regression, where you're trying to find the line that best fits some data points. It could be, say, the support vector machine, where you're trying to find the hyperplane that best separates two different set of points. And it could be a neural network, which is basically approximating a very complex nonlinear function with the various layers in the nodes. Regardless of what model you pick, you basically have to train the model, right? And training the model is essentially an optimization problem. You have some variables, or for the model, you might call them model parameters. Those parameters have some constraints. Basically, they have some permissible values that they can take on. And then you have an objective function. The objective function is basically what tells you the performance of your model. If you're trying to maximize the objective function, it probably represents something like accuracy. If you're trying to minimize it, in which case it's also called the loss function, the error function, the cost function. It is basically a measure for the difference between the predictions that your model is making and the actual values that they represent. Now, to train a model, the classic approach is an algorithm called the gradient descent or the batch gradient descent. What it basically does is it passes all the data points through the model, and which spits out the predictions for those data points. Now, it computes the difference or the error for all the different data points and what the actual value should be. So the error in your predictions, and then it computes the gradient. The gradient is basically the direction in which, if the model parameters were to be moved in that direction, would minimize the error for that data point. And it takes an average of these different gradients and multiplies it by the learning rate, which is a coefficient that is supposed to, say, dampen or amplify the step that the model parameters are taking in the direction of the gradient. Set the learning rate too small and the model will take a very long time to converge. Set it too high and it'll just bounce all over the place and have a very hard time converging. So this is sort of like a problem where you have to find the Goldilocks learning rate for your model training, right? And then you're supposed to repeat this process of the model making predictions, compute the error, find the gradient, take the average, multiply it by the learning rate, and take a step in that direction. And you keep doing this over and over again till the model converges. Converging being that there's no significant improvement in the performance anymore. So that's what the gradient descent algorithm does. Now, how does this algorithm fare against modern machine learning problems? Well, as it turns out, it doesn't fare too well. First, gradient descent is an offline algorithm. which means that it requires the entire data set to be available on hand at once for it to do the training process. However, most machine learning problems today often have streaming data sets, which means that the data is coming in on the fly in real time, and then you have to process it, train the model, and then move to the next data point. So that's the first shortcoming of the gradient descent algorithm. The second is, modern machine learning problems have very large data sets, right? There have a lot of data points in them, which makes gradient descent a very computationally expensive algorithm to implement, because there's just so many points that you have to compute the gradients for, and then it's just pain in the ass. And many times the entire data set doesn't even fit in memory of the machine that you're working on. So gradient descent is not the optimal answer. Hence, we have the stochastic gradient descent, also known as the incremental gradient descent. How does this differ from the gradient descent, which is also called the batch gradient descent? Is that instead of using the entire data set when it's computing the gradient and taking the gradient step, it uses either one randomly selected or some randomly sampled data points from the data set that you're working with. So what this basically does is reduces the computational overhead that you have, number one. And number two, it can then process the data in an online fashion or in a streaming fashion, that the data can come in. It doesn't require the entire data set at once. It can have just some point or some points from the data set, and it can compute the gradient, take a step, right? So hence it fares much better against modern machine learning problems, because one, it's an online algorithm, which is basically the fancy way of saying that it can handle streaming data, that the data comes in, it computes the gradient, does the gradient descent step, and then throws the data away. It doesn't need to keep it. And it can work for very large data sets also, because you're only computing the gradients for some small subset of all the data points. So it's far more efficient compared to the batch gradient descent. And the stochastic gradient descent is basically like the de facto standard for training machine learning models today. And once you've trained the machine learning models, you make predictions using those models. And herein lies the rub. Because when you train something using the stochastic gradient descent algorithm, and as the name would suggest, stochastic gradient descent, there's some element of randomness involved, right? And what that basically does is it yields a degree of noise in the predictions. So if you were to take the same data set and run the stochastic gradient descent multiple times, it could be that in different iterations, you have very different answers to the same data inputs. And the authors of the paper actually conducted an experiment, or conducted a test to test this more formally. What they did was they got a data set from the UCI machine learning repository. The name of the data set was the adult data set, but it's not nearly as raunchy as it sounds. It's just 100+ features that you try to use for a binary classification problem. We're trying to predict whether the person's annual income is more than or less than $50,000. So they, I think they did like 500 different iterations of the stochastic gradient descent for that data set. And what they found was that there's a very high degree of variability in the answers across the iterations. And in some degree, in some iterations, the variability could be as high as 50%, which means that your model predictions are no better than just a coin flip, right? And given that machine learning is becoming more and more a part of mainstream applications, this kind of uncertainty in predictions cannot go unaddressed. And that is basically what they try to do with the HiGrad algorithm. So it's sort of like a different way of looking at things. It's sort of a different paradigm. So far, the way we're all familiar with these machine learning problems, you have some ground truth, the actual value of some data point. Say in this case, it's 6.9. Your model makes a prediction for that value. Say the model predicts 6.4, right? And this is usually what we'll be working with, the actual value, and which is y, and the y hat, which is what your model predicts. What the HiGrad algorithm does, and what the authors propose, and others have also proposed in other ways, is the idea of attaching confidence intervals to these predictions. So instead of just saying that the model thinks the answer is 6.4, the model will say that I think the answer is between 5.5 and 7.3 with a 95% confidence. And this, is that confidence interval, and the length of that interval is a quantification of the uncertainty of that model's prediction. If it's a very wide interval, you know that this model isn't very confident about what it's predicting. If it's a fairly tight interval, you can be more confident about the predictions of the model. Now, given we're working with confidence intervals, one term that you should be familiar with is coverage probability. Now, it's a very fancy term to denote something fairly simple. When you're working with confidence intervals, you're going to specify an interval for the value. And whether the true value falls within that confidence interval or not is basically, the it's basically the success or failure of that confidence interval. The coverage probability is essentially the probability that this happens. So over multiple iterations, it tells you whether the true value falls within the confidence interval that you've proposed. So in this image, you can see, so there's like a lot of data points on the screen, and the ones in yellow. So there's like the point itself you could think of as the prediction, and then the wicks that you see above and below the point are like the confidence interval. And basically all of these predictions are for the zero mean data, right? They're just all trying to predict zero effectively. So all the ones that are yellow essentially do include zero in it in the confidence interval. So they're all good. So they're correct. However, the blue points do not include the zero. So all of those confidence intervals are wrong. And say if you're correct 95% of the time, the coverage probability would be 95% or 0.95. So that's a term to be familiar with, given we're working with confidence intervals now, and is basically a test for how well those confidence intervals work, and is one of the metrics that the authors even use in the paper to judge how well the HiGrad algorithm and certain configurations of it do. The other one that they use is called informativeness, which is basically a measure of the length of the confidence interval. For example, in this case, 5.5 and 7.3. So that's like 1.8 is the length of this interval. And if the interval is wider, the prediction doesn't really have much information in it, right? So if you know the answers are going to vary, the answer is usually going to vary between 0 and 10. And the model spits out a confidence interval that it says, I think with 95% confidence that the answer is going to be between 0 and 10, and it isn't really telling you much. So that's basic. However, if it says the answer is probably going to be between 5.5 and 5.9, then this is like a far more informative prediction than just saying it's between 0 and 10. So another metric to keep in mind that the authors also use in the paper. So now we get to the actual algorithm and the associated Python library. The algorithm called hierarchical incremental gradient descent. It has this very fancy logo, which I'm pretty sure is unofficial. It was on the GitHub page of the R library that they have for the HiGrad algorithm. And I really liked it, so I kept it and I put it on my GitHub page also for the HiGrad Pi. So, and it actually very well represents what happens in the algorithm. Basically, the prongs of the trident represent the different threads that the SGD splits into. So this is the HiGrad algorithm itself, formally like written down in pseudocode. I won't go into the math behind the algorithm as much, simply because I feel the authors can probably explain the math much better than I can. So if you want to learn what happens under the hood, I would point you to the 50-page research paper that they have on the subject, and like the 100+ slide presentation that one of the authors has on the subject. So that's where you should go if you want to thoroughly understand what's going on with the algorithm. my objective here is going to be giving you a more intuitive overview of what happens, and then showcasing the library itself. So this is what happens in the HiGrad algorithm. It starts out the same as any other stochastic gradient descent. So the HiGrad basically builds upon, so incremental gradient descent is basically stochastic gradient descent. So that's the same as what we have already discussed and what you're familiar with. The hierarchical part is where the novelty lies. So it starts out the same as the usual stochastic gradient descent, and up to some number of iterations, post which it splits into multiple threads, right? And the number of threads it will split into is a hyperparameter that you choose. Even the number of steps it will process as a singular thread before it creates the first split is also a hyperparameter. And those I'll get to in a bit. So basically, it starts out as the usual stochastic gradient descent and then splits into two or more threads, right? And now, so this is like, say, level. So we were at level 1. Now there's level 2 of this of the algorithm's training. Now these individual threads can further split into more threads. Maybe they split into 2, 3, 4, or more, and could be they both split into the same number or different number of threads further. And all of these are hyperparameters that we set for the algorithm. And now what happens is, so there are multiple levels, and so basically these are the hierarchy across the training that's going on. So there's level 1 where you had just one thread, then level 2 where it's split into 2 or more, and then when each of them splits into furthermore, you have level 3 and 4 and so on. So this is where things get fun. So what happens instead of taking so how do the things change? First up, how does the gradient step change? So instead of the gradient step being, just one singular instance, it's now multiple threads where each of them has some, gradient step as per its own thread. And we take the weighted average across those within the same thread. So for each step within the thread, and then we take the average across all threads, right? So I don't know if this diagram is making sense to you or not. So if we just look at, from left to right, the first piece, so to speak, the second piece, that is the one above it, and the third piece, that's the one above that. So these three threads. So they're not really three threads. It's basically the same thread with three different pieces. So we take the weighted average of the first piece, the second piece, and the third piece, the respective gradients. And this weighted average is then averaged across all the different threads, the 4 threads that we have in front of us, the 4 leaves, so to speak, right? So this is basically a tree, and those endpoints are the leaves. We take the average across those, and that is going to be the gradient step now. So much more fancy than the standard, the vanilla stochastic gradient descent. How the inference changes, which is basically how does the model make a prediction. Instead of giving you its usual prediction, it will now run a prediction through each one of the threads, and it'll take the average of all of them. And using those, it'll also, and again, these are non-trivial in the sense that it's not, it's not like just some basic computation. It includes like the correlations and the covariances and the standard errors, and then creates like a confidence interval for the prediction above and below the estimate. So so each time when you ask the model for a prediction, it not only gives you a prediction itself, it also attaches a confidence interval to it. Yeah. So another thing to understand within the algorithm, and this is like the two most important hyperparameters of the HiGrad algorithm, and the underlying ideas being contrasting and sharing. Contrasting is the idea of having many different threads in the training, and in the model, which all contrast, the different values, right? So each one of them will give you a different prediction for the same data, data point, and then contrasting these, you'll construct the confidence interval. Sharing is the idea of sharing the gradients across these different threads, and then computing the average to take a step, with the gradient descent step. So contrasting requires more and more threads, and so the two hyperparameters here are how long do you wait before you split, or you start splitting into threads, and how many threads just does each branch split into. So the more contrasting you have, the less sharing there will be, because when you have like a lot of threads, and there's a lot of gradients, so there's not much weight to each gradient. However, when you try to increase sharing, in which case you have lower, lower and the lesser number of threads and longer threads, you'll have lesser contrasting also. So this is where you have to strike the balance, and we're back to that Goldilocks situation that we did with, say, the learning rate, or you could think of, say, the bias variance trade-off. So contrasting and sharing is another one of those tug of war problems where getting more of one means less of the other. So yeah, this is basically something to be aware of, and I'll show you an example with the data that better demonstrates this visually. Yeah, so that was basically the overview of the algorithm itself, and what does it effectively achieve, right? So as a practitioner, what do you care about? Number one, it retains the online nature of the vanilla stochastic gradient descent, so that's a plus. And the best part is it's at the same computational cost. So even though my explanation of it, or on an intuitive level, it might seem like, because there's a lot more going on, this is going to be computationally more expensive. However, it's not. It's the computational cost is the same as a vanilla stochastic gradient descent. So essentially, all this additional information about the confidence interval that you get is for free, right? Computationally speaking. So, and everyone likes free stuff, right? So that's a good thing. Number two, instead of just having the estimator, which is like the prediction that you would get out of the vanilla stochastic gradient descent, you get the estimator plus you get a confidence interval attached to that estimate. So that's number two. And number three is that the estimator that you would get is almost as accurate as just the vanilla stochastic gradient descent, right? So you aren't really losing out on anything, and you're getting the confidence interval information. And also, as a bonus, the HiGrad algorithm is far easier to parallelize than the vanilla stochastic gradient descent is. So that's another plus. Now, getting to the library itself, it's already uploaded to PyP or PyPy, depending on how you pronounce it. So you can do a pip install HiGrad Py and fetch it. So we're currently on version 0.17. The picture on screen is outdated. So you can easily install the library. And with the library itself, the API, I've tried to keep it as similar to scikit-learn as possible, because if you have any experience, or even if you've done any basic course on machine learning with Python, you've for sure been introduced to the scikit-learn library, and the scikit-learn API is like the standard, right? That you create the model, you do model.fit, and you do model.predict to get the answer. So the HiGrad Py API works in the exact same way. You import the model from the HiGrad Py library, you create the model object, you do model fit, you do model predict, and you're done. So now going over the actual library itself, when you're initializing an instance of the model, there's a lot of hyperparameters that you can set, like with any other machine learning model. I won't go over what all of these are. They're fairly exhaustively explained in the documentation, which you can go through. or you can just the doc string will tell you all of this information too. I don't think I have the documentation up yet, so just go through the doc string. And it's not, and also bear in mind that HiGrad is currently only implemented for linear regression and logistic regression, which is basically what the HiGrad library in the R library that the authors had created was implemented for. So I've also only implemented it for linear regression and logistic regression. Hopefully in the future we'll extend it to more to other machine learning algorithms and machine learning models and make it even more useful. So yeah, so these are like the different hyperparameters that you can set. And once you have that, in this case I've just created a dummy data set and split it into train and test data sets. You fit, you predict, you can use you can score it also, and it automatically figures out, if it's a linear model, it'll give you I think I think it was the mean squared error, and if it's a logistic model, it'll give you the accuracy. And when you make the predictions, you'll get your y hat, and you'll get an upper and a lower bound for the confidence interval. And basically that is as promised by the HiGrad algorithm. So this is what it will look like. I've just plotted it. So in the white, the lines that you see are the upper and lower bounds for the confidence interval. In this case, I think it's the 95% confidence interval. You can change that as a input parameter, as a hyperparameter of the model. And if you look at this plot, you'll see how many times so basically the coverage probability of this is pretty decent, and many times the red dot, which is the actual value, the true value, falls within the confidence interval that the model has predicted. Sometimes it doesn't, but that is to be expected. So yeah, and in this slide I basically have 4 different plots for the same data set, but different hyperparameters for the number of splits and the number of threads. So the number of splits is how many times the tree is going to split, and the number of threads is how many threads each thread splits into. So 2 splits into 2 threads is basically the splits will happen twice. So starting with a singular thread, they'll split into 2 threads each, and each of those 2 will split into 2 threads each. When I set the number of splits to 3, the same thing will happen 3 times. So 1 splits to 2, 2 splits to 4, 4 split to 2 each to 8. Right, and you can see how the confidence interval and the predictions change for each. And as you increase the number of splits and the number of threads, the confidence interval starts becoming much tighter, which, depending on what you're doing, might be a good thing or might not be a good thing. So you have to compute the coverage probability of this. I think I can turn that into a function also and make things easier. So yeah, I'll actually add that, adding coverage probability as a function that you can call. Yeah, so that's about it. And one thing to bear in mind about the number of threads that you split into, when you're first thinking about the idea of first exploring this, and it did for me also, the idea of splitting into a lot of threads seems like an obvious thing to do. However, that is not a very good idea, because it just increases the bias that you have in your predictions, and it doesn't really yield very good numbers. And in the paper also, the authors have gone over how, in most cases, 4 or less threads are going to be sufficient. The number of threads that you split into, keeping it 4 or less than that is probably sufficient. And 4, I think, was like the optimal number. But just to be sure, I'd suggest you go through the paper once. So yeah, that is it. You can reach me on any of these via email, Twitter, or you can go to my GitHub, where the library is hosted. And yeah, I hope you enjoyed this, and I'll see you guys in the live Q&A session. Bye bye.